This short video is going to explain how seismic waves can be used to determine what the material inside the earth is made of. So here's a part of the earth here. That's the surface of the earth. There's my proverbial tree. And when an earthquake occurs, it produces seismic waves which radiate out in all directions. And some of those waves, let's say this is the source of the earthquake, some of those waves go into the earth and then they curve and come back out where they can be recorded by a seismometer at some kind of seismic station. Let's say this blue area here, that's my seismic laboratory that's recording the seismic waves produced by the earthquake that travel along the path in purple. And as those waves go through the earth, they pass through different depths of the earth. And by studying the seismic waves produced by many different earthquakes, some of which are shallow like this, and some of which go very deeply like this, the geologists or seismologists can determine the properties of individual layers of the earth, the velocity with which those seismic waves pass through the different layers of the earth. So for example, they might find that the seismic waves that are going through this layer of the earth right here might have a velocity of, let's say, 4 kilometers per second. And those waves which are going through this layer of earth down here, the deeper layer here, might be going 5 kilometers per second, etc., etc., etc. And then they use those seismic velocities, the velocity with which the wave is moving through the rock, to infer the type of rock. And we've said that in a simple sense, we can relate the velocity of the seismic waves to the density of the rock, with the simple relationship that the denser the rock, so this is a simple rule here, denser the rock means the faster the wave travels through that rock. Okay, so in a simple sense then, the seismologists determine the velocity of the wave through individual rocks at individual layers, and then they correlate those velocities with the density, and then they tell us, okay, well, the only plausible rock with a required density would be, say, gabbro, or would be, say, peridotite, or whatever rock type they infer to be there. Now, in fact, this story is a little bit more complicated than that. So let me delve into it a little bit. I won't take a lot of time to do it, but I want to explain at least the true story of how the seismic wave velocity is related to the rock type. So the first thing to understand is that there are actually two kinds of seismic waves produced by an earthquake source. And those are called the S or shear wave and the P or primary wave. And here's what they look like in animation. Okay, the upper animation is the P wave, and you can see that as the P wave travels or propagates, it alternately compresses and then compresses the medium in the direction of propagation, which in this case is from left to right. So the particle motion is shown by those little arrows there, is in the exact same direction in which the wave is propagating through the medium. The S wave shown below, it's a little bit more difficult to see, but if you study the animation, you can do it. You can see that as the S wave propagates in the same direction as the P wave from left to right, it induces motions or distortions of the medium that are perpendicular to the motion of propagation. So they're indicated by the direction of the green arrow, in this case up and down. So the particles actually move up and down to create the passage of the wave, which in this case is going from left to right. So the P wave and the S wave are both produced by an earthquake source, and both of those waves then travel through the earth and will travel along the paths indicated here by the pink lines. Now, if we actually look at the equation, so once again, the seismologists can determine from analysis of the arrivals of the seismic waves the velocity of both the P and the S waves as they have passed through a given layer of the earth. And the question then is, how do we relate that velocity with a certain kind of rock? Now, the actual expressions, the actual equations, that relate the seismic wave velocity to the properties of the rock aren't as simple as just seismic wave velocity is proportional to density. In fact, this is what the actual equations look like. The velocity of the P wave, Vp, is given by a relatively simple equation that says it's equal to the square root of a property K called the bulk modulus of the medium plus 4/3 times mu, which is another property of the medium called the shear modulus, divided by the density. And I'm going to write the expression for the S wave velocity here just so that I can see them at the same time. So the velocity of the S wave is actually a little bit simpler. It's just simply equal to the shear modulus mu divided by the density. So these are the actual expressions then that relate the velocities of the seismic waves to the properties of the medium, including the density. And the first thing you should notice is that, well, wait a minute here. The density is inversely related to the seismic wave velocity for both P and S waves, right? So in other words, as the density increases, the seismic wave velocity should decrease, not increase. So that simple rule I showed you earlier should be invalid. Well, what's going on here? Well, it turns out that what's going on is that we have to pay attention to what these other values are, these other properties of the medium, the bulk modulus and the shear modulus. The bulk modulus is simply a measure of the stiffness of the medium. The stiffness of the medium. So what it basically does is it takes a medium, some kind of rock, and you try to squish it or compress it, and then you compare the initial volume of the material to its volume when it's compressed. And that is equal to what the bulk modulus is. And you can see that when that value, when K is close to 1, that's saying that the medium has compressed very little, or it's a relatively rigid or incompressible medium. This is a rigid medium. Okay? When K is smaller than 1, that means that the medium has compressed quite a bit, or somewhat, and therefore in its compressed state it occupies less volume. The shear modulus, mu, does a similar thing, but it considers the distortion of I'll say a block of rock here, and then we apply some kind of shear stress to it, and that will cause the medium to deform. And so it looks at the degree of deformation that's produced by these shear stresses and compares the original undeformed state with the deformed state. And once again, the idea is that when mu is approximately equal to 1, there's very little distortion. So once again, the medium is rigid with respect to shear stresses. That is, when we apply shear stresses to it and we try to deform it as shown here, it doesn't deform very much. Whereas a medium with a relatively small value of mu deforms readily when we apply shear stresses to it. So the bottom line is that these two properties of the medium, K and mu, these compressibilities describe the resistance of the medium to deformation. And when they're relatively high, we can consider the medium to be rigid, and when they're relatively low, then the medium is more deformable. Well, this then is the explanation for what's going on, is that although the densities of rocks change a little bit as you go from, say, granite to gabbro to peridotite, what really changes significantly are their elastic properties, K and mu. So in other words, if I were to plot up, there's sort of a correlation between these elastic properties. So if I were to plot, for example, the density of rock, all different kinds of rock, versus either the bulk modulus or the shear modulus, I would find that the graph looks like this. So in other words, as the rock gets a little more dense, its elastic properties become higher. In other words, it becomes a lot more rigid, a lot more rigid. So even though the density may change only 10%, the rock may become maybe 50 or 70% more rigid than the previous rock, than the lighter, the less dense rock. So in other words, in these expressions then, the factor that dominates the properties of the seismic wave velocity is not the density, it's actually the seismic wave velocities. So as we go from, for example, granite a rock with a relatively low density, let's say the density of granite is maybe 2,600 kilograms per meter cubed, okay? Well, this is the density here, sorry. It's density here. We find that its P wave velocity, given that density and its elastic properties, is about 5 kilometers per second. And its shear wave velocity, or S wave velocity, is only about 3 kilometers per second. Right? Now, if we then go to, let's say, basalt, a rock which is denser, so its density is more like 3,000 kilograms per meter cubed. The thing is that basalt has a much higher bulk modulus and much higher shear modulus. In other words, it's a much stiffer rock. So when you calculate the seismic wave velocities, they're actually higher. So in other words, the effects of the more rigid rock overcome the effect of the slightly larger density in the equation. And we find that the P wave velocity is about 5.5 kilometers per second, and the S wave velocity is about 3.2. And finally, if we were to go to a rock, say like peridotite, right, which is the densest rock, the rock of the mantle here, that might have an average density of, say, 3,300 kilograms per meter cubed. It, however, is a much more rigid rock, and so its P wave velocity is much greater at about 8.5 on average, and its S wave velocity might be about, say, 4.5. So once again, the effects of rigidity are dominating the effects of density in the equations here. So even though we look at the equations and we go, oh, okay, it should be obvious that if the rock gets denser, its velocity should go down, that's actually not what happens, because although the rock is getting denser, its seismic properties, its stiffness, its elastic properties, its stiffnesses are getting much higher. And so it's these factors, let me give them a different color here, it's these things in pink here that are actually dominating the equation and explaining why we had that simple rule, which still is valid, right? That the denser the rock, the faster the wave. But we probably should rewrite that then to be more accurate, as the true rule is the denser the rock means the stiffer the rock, more rigid, and it's the stiffness more than the density that creates the faster seismic velocities, faster the wave. So this is sort of the more accurate, more true version of that simple relationship, which is still valid, that the denser the rock, the faster the seismic waves travel through it.